This is the last video in section 15.1, double integrals over rectangles. I want to pick up where we left off, seeing just how easy these double integrals really are to compute once you've got them set up. We'll see setting them up is actually going to be more trouble usually than the actual integration. So here I want to see what is the process that we go through to actually compute these double integrals and go through a few examples to demonstrate that. And I've drawn a picture here. It looks kind of complicated, but I think we can talk through it. A picture here to explain the idea. So I would say that our double integral we know is the volume below the graph, which I have in blue here. I've drawn these vertical columns down just to kind of represent the volume we're finding under that blue graph. But the blue curved surface up here, that's our functions graph. And if we take a look, sorry, that's my cat making noise if you're hearing things. That will probably continue, unfortunately. Let's jump back in here. So yeah, let's look. This double integral is really the volume below this graph above that rectangle R. And if I've got it labeled out like this, we can see that's really just the same as, if I take a look, we can consider what would happen at any given x value here. Could we figure out a function that gives us, in terms of x, what is this cross-sectional area of this volume? If we take that cross-sectional area, which I've thought of as being a of x, then integrating that area from a all the way out to b, the values our x's run over, we'll pick up this little slice for every little place between a and b, meaning we can rewrite this as that area times that little amount of thickness dx makes a little infinitesimal piece of volume. We take that for every value between x equals a and x equals b, and we get that total volume, the same as the double integral. And so I want to explore this idea because this actually gives us a nice way to evaluate these. All we have to say then is that, what is this area a of x? Well, let's just look. The area a of x should just equal, just thinking of this picture, just thinking of this picture, right? It should be what we get when we integrate this function, which is really just the same as f of x, just frozen at this x value and letting y actually change. So all we actually really have to do is think of holding our x value fixed in our function and just integrate with respect to y from c where it starts to d where it ends. That picks up the area under this red curve above this little solid black line I drew here through the rectangle. So c to d. So all we have to do is think of this x as being fixed at whatever value we're currently located at, and actually integrate in the y value. Just hold x fixed, hold x fixed, integrate with y. Well, then all we have to do is plug in this expression for a of x over here, and we get this. And so this is the type of double iterated integral I mentioned at the end of the last video. When we actually write out, instead of just a dA here, when we write that out as in terms of the individual differentials, dx and dy, the changes in the different directions, then we call this, and we put those, the integral bounds for each variable on these integral signs, and we call this a double iterated integral. And I want us to note that the inside integral bounds go with the inside differential. So these are our y bounds, c to d, and the outer go with the outer. Now it turns out in this argument, it seems pretty obvious that you could do this in reverse. You could come up with what I've got here in green. This cross section here, where we think of stop at a general y value and say what the area, the cross-sectional area is there, then integrate that with respect to y for all those y values, c to d. That would pick up the volume of this little weird shape too. But then if you did it that way, you could think of, to get that cross-sectional, that green cross-sectional area, you just integrate x from a to b and hold the y value fixed. So you might say you could do this in reverse. You might write this as this. And for the picture I've drawn, this would work. And notice that the x integral bounds now still go with the inner differential, which is x. Same with the outer bounds going with the outer differential, dy dx. So it turns out that for a rectangle like this and an integrable function f, all we have to do is write this out as an iterated integral. And integrate holding one variable constant at a time, working from the inside out. This is called partial integration, by the way. I'll write that down. This idea here is called partial integration. And that's what we'll use. So we might notice here, this looks kind of maybe familiar, that it's saying we could integrate the x first and then the y of what remains, integrate in y for what remains, or we could do the y first and the x. We need to work from the inside out, but we have those options. And so you might notice this looks kind of familiar. This looks kind of like the flip side to Clairaut's theorem that let us take partial derivatives in either order. This is saying it shouldn't matter which order we anti-differentiate, which order we do partial integration in. And there's actually a name for this fact. I'll call this, the name of this is Fubini's theorem. And it just states pretty much that. I'll skip some of the details, but if f is continuous on a rectangle a to b in the x direction, c to d in the y direction, then we can write this the same both ways. In fact, let me see if I can do this nicely. It's just saying this result we already have. Okay, that's not working out. Okay, no worries. But it's just the same result that we can integrate in either order. This might not be super clear what we're saying yet, but I think it'll be very clear with our first example, just coming right up. So let's see an example. Let's see a few, in fact. Let's evaluate some of these double integrals. We'll write them out already iterated. For example, 0 to 1, 2 to 3 of x minus y squared dy dx. Right. So this isn't so bad. All we're going to say here is that first let's integrate the inside stuff with respect to y and just leave the x like a constant through this integration. So when we do that, we get, might want to pause here and see if you can do this step. But when I do it, I get, it looks like negative x minus y cubed over 3 evaluated from 2 to 3. That's what I get from the y integration. And let me be clear, I'm saying the y value is being replaced by values from 2 to 3. Right? This is the same thing we'd get if we just had like a 1 here instead of an x. That comes along. You can check the partial derivative. Then we take the partial derivative with respect to y of all that mess. It does give you back what we started with. Check that. It's a good thing to check. But if we get this, then we're really just plugging in. At the top bound, we're plugging in y equals 3 into all this mess. So we get negative, let me set up brackets, negative x minus 3 cubed over 3. That's what we get at the top bound, because y is replaced by a 3. And at the bottom bound, we get, let me make it very clear, x minus 2 cubed, negative x minus 2 cubed over 3. And this all still needs to be integrated in x. I forgot that back here. This is still, x is still being integrated from 0 to 1. We haven't done that yet. This was a y integral result in brackets here. This result in brackets is still just that y integral. And so from here, I would clean this up a little bit. I'd make this easier by factoring a negative out of everything, and probably a 1/3 as well. And then you're still integrating from 0 to 1, x minus 3 cubed minus x minus 2 cubed dx. Keep that negative 1/3 out front, and I'm just going to blow through this as quick as I can. Usual Calc 1 integral here, right? Integral from 0 to 1 of some x stuff. That's Calc 1. I'm just blowing through this. You can check my results. Oops. This is evaluated from 0 to 1. So it looks like we get negative 1/3. At the top bound, I get negative 2 to the 4th over 4. In fact, let's show a little trick here to make this a little bit easier. If I want to do this by hand, I'm going to factor that 1/4 out to the front, put it with the 1/3 to make a 1/12. It's a little easier to evaluate what remains once we've done that first. Let's free up some space. So it looks like we get, at the top bound, negative 2 to the 4th minus negative 1 to the 4th. At the bottom bound of 0, we get negative 3 to the 4th minus negative 2 to the 4th. Which you can clean up all you want. Looks like we get 16 minus 1 minus 3 to the 4th is 81. Oops. Minus 16. And so on. Right? Arithmetic from here. I hesitate to even show it. Let's see. Looks like we get 1/12 of 50. There's 25. Yeah, 6. Boy, that was unclear. 25/6. So it looks like this is what I get. And you can try this in the opposite order. You'll see you get the same thing. Right? You can switch this around. You could also write 2 to 3, 0 to 1, x minus y squared dx dy, and get the same result. If we didn't mess up our previous result up here already. I should say this implies. Okay. So let's see another couple examples, and we'll end the video after that. Yeah, let's see this one. Let's say we've got the integral Again, maybe 0 to 1 and 2 to 3. But this time let's do xy quantity squared. Let's say this is dx dy. Right. So let me first say that we could do it kind of similar to what we did before. We could integrate the inner stuff first. Just integrate the inner stuff, the x stuff, and treat that y value inside of there like a constant, just like you had a number there. I think if you do that, you would get I think this is what you'd end up with. And this would be evaluated from x equals 2 to x equals 3, whatever that gives you, integrate from 0 to 1 in y. So let's not take this all the way, but let's see what happens here. It looks like I could pull out a 1 over 3y, xy cubed from 2 to 3. Let's see what happens from these brackets. At the top bound, I get x. Keep in mind, these are x values we're plugging in. So we get x equals 3 gives me 3y cubed. X equals 2 gives me 2y cubed. And that's what we're integrating in y. We bring the 1/3 out and distribute the y. Oops, forgot my 1 here. And notice I can factor out a y squared, leaving 3 squared minus 2 squared, 27 minus 8, which is 19 dy. And from here, it's pretty simple. And I don't even care to finish this. I just want to show that this got kind of complicated here, and we can avoid this. Here we had to deal with this extra y in the x integration, and be very careful here with this partial integration. I think it's easier to do this first. In fact, let's see how easy it is. From here, let's notice I can write xy squared as x squared y squared. Right? That power distributes to the x and the y. It doesn't distribute, but it's kind of like that. Then we get really the x integration that's on the inside sees this y squared as a constant. And you know that you can bring a constant outside of the integral, outside of the x integral at least. So you could rewrite this. You could bring out that y squared to the front of the x integral, right? Y looks like a constant to the x integral. But notice now you've got this integral 2 to 3 of x squared dx. And if you compute this, keep in mind what you're going to get. That's the area under the x squared curve from 2 to 3. That's just a number. Right? No variable here. After you compute out the value. So this is just a number. This can actually come out of the y integral because it looks like just a number, a constant as far as y is concerned. So I'll pull that outside of this whole parentheses off integral. I'll pull that out to the front of the y integral to give me, right, this is just some number out front multiplying on what remains, 0 to 1 y squared dy. And so we see that we were able to break this double integral in two variables up into two single variable integrals. I would call this a separable integral. Just meaning we can separate it in this way, because now it's easy. Now we can say, if we call our original integral I, we can say it really just equals handling the first integral here times the second integral pretty easy to compute here. We get 1/9 from both the 1/3 copy, the copies of a 1/3. It looks like we get 3 cubed minus 2 cubed. We've already seen that's 27 minus 8 is 19. And y cubed from 0 to 1 just gives me 1. So we get 19/9. Quite a bit quicker than we got our other answer. Right, so you want to look for this ability to separate these out. It's very nice. Let's look at one more example down here. Let's look at this example. Let's find the volume under the graph of this equation and above this rectangle r equals -1 to 1 in both directions. So maybe first we start by visualizing. You might notice this equation, it's written in maybe a strange order, but this is just a sphere centered at the origin, radius 4. And we're saying we want to keep what's below that graph, but above this rectangle in the xy plane, -1 to 1 in both directions. So just to draw it out very roughly, really not going for much detail here, we have this -1 to 1 rectangle sitting down flat in the xy plane. And we've got this, and notice this goes from, said it, but this goes from -1 to 1. So across, it's only 2 units across. This sphere is 4 units across, right? It's a radius 4. So it's going to look something like a lot bigger and we're just keeping what is above this rectangle but below the sphere. So I've kind of run out of room here with my picture. Let me back up a little. Do this a little smaller. Let's say it's only this much bigger. What's happening is we're going up to this thing and then we're stopping. So what's going to happen is you're actually going to get this sort of weird volume that gets cut out of that. And then all this other stuff disappears. Now, this is not to scale by any means, but this gives you a sense of this solid object. We've got this kind of spherical cap over this rectangle R. So let's see how we would do this, but notice our function here, right, is usually described as z equals f of xy. But in that case, it's just our z value in this equation, so it's going to be the square root of 16 minus x squared minus y squared. That's what I get if I just solve for z in this equation. You do get a positive or negative square root when you do that, but I'm taking the positive root because I want what's above my rectangle but below the surface. That keeps me up here, not in this region below where the graph also extends. Right? That sphere extends down here as well. But I took the positive, maybe I'll note that, because my region's z region is positive. And then so all we have to do is, to find the volume, we need to integrate over that rectangle R this root. Right. So let's see, and this is with respect to area, dA. This is easy to write as an iterated integral, since both of them are the same. It's easy enough to write it this way. But now, what am I going to have to do to actually integrate here? You might want to think about this for a minute, maybe even pause it and think, see if you know how to get through this. you would have to do, oops, some sort of trig sub. Right, this is kind of strange here, but you'd have to consider one of these a squared minus x squared trig subs, where your a value is the square root of 16 minus y squared. Anyway, something to consider. But maybe I'll leave the integration to you, but something that'd be nice to do here is at least simplify the situation. Notice we could write things as, just looking at our volume here, we could just go from 0 to 1 in both directions. And if we did that, we'd just get this kind of front corner of our shape. We'd get this corner, right? From here to here to here and here. We just get that corner. So we could just take that corner only and just multiply by 4. By symmetry, we're going to get the same thing everywhere in the other 4 corners, but now we only go from 0 to 1 in each of these. I mean, this doesn't help you much with the actual integration. It's still a mess here. You still have to go through some sort of trig sub to do this. But at least you don't have to deal with the ugly bounds. Okay. Maybe one quick last one to remind you of some integration techniques before we stop here. Like I said, with that last one, you can try the trig sub. That's not really the focus, but I want us to see what sort of techniques might work for that. So let's look at this last example. Let's just say it's the integral from 0 to 1 of xy e to the x squared plus y squared dx dy. Well, you could jump into this and do a substitution. I want to see how that works. Let's let u equal x squared plus y squared, remembering that our inner integral is with respect to x, and we're always doing that first, the inner integration first. So I'm considering the y squared here and the y here as constants. If I let u equal x squared plus y squared, I want to know what dx is, so I differentiate with respect to x, and I get du is 2x dx. Then I could replace this. Notice the x integral sees this factor of y as a constant. I'll pull that out front. And now I'm just trying to replace these remaining pieces of the x integral with some u expression. And if I do that, it looks like my new integral bounds, plugging in x is 0 at my lower bound. I get u goes from y squared up to, with x plugged in at my upper bound, 1 plus y squared. Right, just plugging in lower bound here, in for x. U is y squared. Upper bound here, in for x. U is 1 plus y squared. The y here we've already brought out front, but the x dx, I can replace that with 1/2 du. Let me put my du out back. Right, and remember, we're just working on this inner integral. Hold the y out front of that. We've still got the y integration later. The e to the x squared plus y squared, that's just e to the u now. And we've replaced all the pieces. The x dx got the 1/2 du. The exponential got e to the u. We changed our bounds. This is good. We could integrate from here. Looks like we get, I'll even pull that half all the way out front. Looks like we'd get e to the 1 plus y squared minus e to the y squared. All times the y that was already out front, dy. And from here, you could do some more stuff. You could call this e to the y squared y, and that actually just leaves behind e minus 1 in parentheses if you factor in e to the y squared out of all this. E minus 1, that's just a constant. I can bring that outside with the half that was already there. Easy substitution from here. Breeze through this real quick. Maybe I use a v since I already used u before. Change my bounds. They actually didn't change, but I wrote the change down. It looks like we get e minus 1 squared over 4. So that'd be our final answer. And that's fine, but I want us to see that we already had to do this substitution down here. Well, maybe I can make it easier and just save doing 2 substitutions, especially this one involving some variable that's playing as a constant. So to avoid that, what could I have done instead? I could do this. Take that original integral, that's what we started with, and pick apart this exponential. Rewrite that part, first of all, as broken up into e to the x squared times e to the y squared. And now notice I can separate that out. All right, e to the x squared plus y squared is just e to the x squared times e to the y squared. It's a nice fact there. And so now this is fully separable. We have a function of x times a function of y. The function of y looks like a constant to this x integral. So I know I can split this up just like we did earlier in the separable integral. I can write this as the x integration times the y integration. But notice here, in a definite integral, it does not matter at all what we call the variable. It's called a dummy variable, actually. At the end of the day, we're replacing these variables with zeros and ones after we anti-differentiate. So the label we use for these disappears at that point. What matters is the structure of this function and the bounds. And notice the structure of the function, variable exponential to the variable squared. That's the same in both of these integrals. They give the exact same value after you plug in those numbers after the anti-differentiation. So this is actually the same thing repeated twice. Which means it's just this single integral squared. Maybe kind of referencing this answer we got over here, you can guess this is probably, and you can work it out, this inner integral has got to be e minus 1 over 2. So that our answer is the same, e minus 1 over 2 squared, which is e minus 1 squared over 4. You can do this easy substitution, but that's just exactly what we did here, right? We've already done it and seen that we did get e minus 1 over 2 quantity squared at the end of the day. Okay, that's it for this section. I hope we saw that double integrals are not that bad once we've got them set up, right? That's really the hard part. Next time we'll see double integrals over more general regions, not just rectangles. How do we handle that? We'll see it's pretty much the same idea, except we might have functions to describe our bounds instead of our integral bounds, instead of just numbers. More on that in the next video.